Hi there, thanks for joining us on a Q&A edition of Space Nuts. Andrew Dunkley here, your host. Great to have your company. Coming up, we've got a few questions. Nick is going to ask about supercharged neutrinos. Andrea is making a return appearance. She's got a couple of questions about the dark side of the moon and shallow craters. And Eli is asking about elements and the speed of objects. And if we've got time, we'll chuck another question into the mix as well. All coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1,
2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And with Fred away, Jonti can play. It's Professor Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Jonti, hello again.
Good afternoon. How are you going?
I'm well. Great to see you. I think we should just go straight into it and hit you with our first question. It's a topic I'm not overly familiar with, but this one comes from Nick. I just read that a supercharged neutrino was detected by the Kilometre Cube Neutrino Telescope, and a theory was put forward that it came from an exploding black hole. Please explain how a black hole can explode. Love the show, Nick. Thank you, Nick. We love that you love the show. Thank you for sending in a question. Exploding black holes. I seem to remember Fred might have written a book about something like that once. But anyway, do they explode or do they merge or do they collapse? Yeah. They eventually disappear. I know that.
Things. Now, straight up, I'm not a cosmologist or a cosmetologist, which I always used to joke about cosmologists being cosmetologists, and then it turns out a cosmetologist is a real thing. So never mind. That's further from my area of expertise. So any answer I give, take with a larger grain of salt. As is always the way, the further you go from your expertise, the more out of date your knowledge is. My knowledge on exploding, or rather evaporating black holes, goes back to basically when I was an undergrad and I was doing lots of courses in lots of different things. Yeah. And this goes back to some of the work that made Stephen Hawking so world-renowned. Now, obviously, for a lot of people, Stephen Hawking became a global name with the publication of A Brief History of Time, which did a very good job of explaining very complicated things in a way that people could at least feel like they had a grasp of. I remember reading it as a kid and it made my head hurt, but in a good way. I could actually follow it. It was well explained. One of the things that Stephen Hawking did fairly early in his career, I think in like 1974 or something, was do some very theoretical work on black holes where he postulated that black holes could lose weight through a process called Hawking radiation. Yep. And the idea is that black holes can effectively be considered to have a temperature and to radiate energy and therefore mass away into space. And the smaller the black hole, the hotter it is, so the quicker it would radiate. And this is all backed up by ridiculously complex physics and mathematics that is way beyond my level of full understanding. But part of the idea behind it is that what we think of as the empty vacuum of space is actually not a true vacuum, but is instead constantly populated by pairs of matter and antimatter particles that spontaneously create and then collide with each other and disappear again. And if such an event happens near the event horizon of a black hole, one of the particles falls into the black hole, the other escapes, and it's seen to lose mass, lose energy, and radiation going along with that. Now, the bigger the black hole, the colder it would be, so the slower it radiates anyway. But also, the bigger it is, the more effectively it can feed from its environment. Even if that's little bits of dust falling in, or if it's near a star, it can feed off that star, get an accretion disk. So the black holes that form in the modern universe are formed by stars reaching the end of their lives and are massive. They're more massive than the sun by a long way. They're formed from stars much more massive than the sun. You get massive black holes, you get intermediate mass black holes, and you get supermassive black holes, and they're all the big whopping ones. And the timescale, as I understand it, for those black holes to decay through Hawking radiation is ridiculously longer than the age of the universe.
Yes.
And they're probably not emitting Hawking radiation at a level that we could detect because they are very cold in his quantification of it. However, at the birth of the universe, when the temperature and pressure was immense after the Big Bang, there were theoretically a class of black holes created called primordial black holes. So these were black holes that were not born from the fiery death of a star, but were instead born out of the Big Bang and the pressures and the temperatures. And these could be black holes down to the mass of a thumbnail, or down really, really tiny ones, planet mass black holes.
Yep.
The smaller you are as a black hole, the more quickly you radiate things away, so the shorter your lifetime. And so you have this idea that these primordial black holes evaporated over time, and effectively none of them will survive to the current day. Those evaporating black holes would evaporate over time and give off radiation that we have never yet detected. But a black hole coming to the end of its life will evaporate faster and faster. There's a quote on an article I found recently which may be tied to this. An article entitled "An Exploding Black Hole Could Reveal the Foundations of the Universe," published from September last year, talking about the predictions that as our technology gets better in the coming years, we may be able to detect this Hawking radiation in an event where the black hole reaches its critical phase and evaporates entirely within the next few years. So not quite the neutrino discovery that we were talking about in the question, but a related thing. And there's a quote here from Andrea Tham, Associate Professor Andrea Tham. I do hate it when articles don't give people's well-earned titles until later in the sentence, or don't give them at all, which is another rant I could go on that's separate, but it particularly affects my early career colleagues, affects colleagues from non-traditional backgrounds and stuff, and it's a very diminishing thing. It lowers their expertise. Anyway, this is a quote from Associate Professor Andrea Tham from University of Massachusetts Amherst. Says, as primordial black holes evaporate, they become ever lighter, so hotter, they therefore emit even more radiation. It's a runaway process until they explode. It's that Hawking radiation that our telescopes can detect.
Yeah.
So what's happening is you've got these primordial black holes that are really itty-bitty ones that are therefore evaporating quicker than they can gain mass. They're beyond this critical threshold. And so you get this runaway death where the more massive ones live longer before they get small enough to finally evaporate and then explode. And so I would guess that the observation of this super neutrino that has been linked potentially to an exploding black hole is not two black holes colliding. It's not a modern black hole formed from the death of stars, but rather is the death of a primordial black hole, as would be predicted by this research by Stephen Hawking more than 50 years ago in the form of Hawking radiation. So that's my thinking on what's happening here. Now, obviously, I am not an expert. I've said previously on many places that in a lot of disciplines, and when we're teaching our undergrads, we often say avoid Wikipedia. Wikipedia is not a static resource, it's a fluid resource, and it's often wrong. And I know for journalists, it's probably often something you caution, don't get your facts from Wikipedia. For astrophysics, and particularly the more technical and hardcore ends of astrophysics, Wikipedia is actually very reliable because very few people will be interested in maliciously editing a web page because, frankly, they'll go after other topics that are more triggering. But also people who are interested in this stuff and have the knowledge tend to be very obsessive, and if they spot something wrong, they fix it very quickly. The result of that is if you Google Hawking radiation, the Wikipedia page is very lengthy, goes into a lot of detail, includes some of the maths that makes my head hurt and makes me want to cry a little bit. I'm talking about black hole evaporation and things like this. Now, the equation for black hole evaporation that's on here, which is based on the Hawking work, gives an evaporation time for a black hole of 2.14 times 10 to the 67 years. So that's 2.14 multiplied by 10 with 67 zeros, multiplied by the mass of the black hole divided by the mass of the sun to the power 3. So if you've got a black hole that is one solar mass, it will take 2.14 times 10 to the 67 years to evaporate. And the more massive it is, the larger that number gets to the power 3. So the multiplier here is get the mass of the black hole as measured in units of the mass of the sun, cube that number, and then multiply it by 2.14 times 10 to the 67, and you get a headache, but you get a number. Now, the mass of the sun is, 2 times 10 to the 30 kilos, right? Mass of the Earth is 5.97 times 10 to the 24 kilos. So that is effectively 2 times 10 to the minus 6 solar mass. It's about a millionth of a solar mass. So we'll just say it's 1 millionth of a solar mass. 1 millionth cubed is 1 times 10 to the minus 18. That means a black hole the mass of the Earth would decay much more quickly. It would decay in only 10 to the 49 years, which is still much, 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 much longer than the age of the universe. But you can play this game with everything. I am too fat. You know, we talk about health and everything on the show before. I am a fair bit more than 100 kilos, but let's assume I was 100 kilos, just because that's an aspirational goal and it would be nice if it were true one day. In fact, I'm 100 kilos and you make me a black hole, I would be sad, but probably wouldn't have long to think about it. At 100 kilos, I would be 10 to the 28 times less massive than the sun, roughly. The sun is 10 to the 30, I'm 10 to the 2, 10 to the 28 is the difference. 10 to the 28 cubed is 28, 56, 84, so that's 10 to the 84. So that means I would disintegrate in 2 times 10 to the 67 times 10 to the minus 84, which is about 10 to the minus 17 years. So suddenly a Jonti mass black hole would disintegrate and evaporate in a tiny fraction of a millisecond. So these primordial mass black holes that evaporate are doing so because they're very small. You could, if you wanted to, and I'll leave this as an exercise to the reader because me doing mental arithmetic is not the most exciting thing. You could work out what mass a black hole would have to be to evaporate after 13.8 billion years, which is about how old the universe is. The reason that's an interesting one is if there were any primordial mass black holes of that mass, and they were to evaporate, they would be evaporating in the very near universe. And that would make them much easier to detect because the intensity of radiation we detect is proportional to 1 over the square of the distance. So if something's twice as far away, it's 4 times fainter. If it's 3 times as far away, it's 9 times fainter. So I don't know. I'm not a black hole expert by any means. I say that all the time. But if there were a black hole of that mass formed at the Big Bang, then maybe they will be evaporating in the relatively local universe, and they're the ones that have been most likely to detect. I do not, however, know what the distribution of masses for primordial black holes would be. It's possibly on this Wikipedia page, but have a look and find out if it's your kind of thing. But hopefully that explains why there's a turnover point where things would decay in less than the age of the universe or more than the age of the universe. And that mass is somewhere between the mass of a Jonti and the mass of the Earth.
Okay. Fascinating. Yeah. All right. Thank you, Nick. And Nick, you might have heard us talking a week or 2 or 3 or 4 back about what they think might be the discovery of a primordial black hole. So that's a story worth looking up as well. Thanks for your question. This is Space Nuts Q&A edition with Andrew Dunkley and Jonti Horner.
0G, and I feel fine.
Space Nuts.
Now, Jonti, we've got an audio question that comes from a repeat offender. Her name's Andrea.
Hi, guys. Got a couple of questions I'm hoping you can help me with. The first question I have is why does the dark side of the moon not have anywhere near as much damage as the face of the moon? My second question is why are the craters so shallow on the moon, considering the size of some of the impacts zones and craters? They all seem to be the same depth, and which is quite shallow, especially if you look at Teo, which is 3,000 miles wide, with an incredibly shallow crater. If you could explain for me why that occurs, that would be absolutely amazing. Thank you very much. Oh, and this is Andrea from Wanneroo. And Andrew, Wanneroo is actually a Noongar or a Whadjuk Noongar people word that actually means the area of the digging stick. Unfortunately, not pet kangaroo, although I have had one of those as well. Thanks, guys. Take care. Bye.
Thanks, Andrea. Lovely to hear from you. I'm glad she explained that. You probably don't know what she's talking about, Jonti, but when Andrea last sent us an audio question and she said she was from Wanneroo, I translated that to an Indigenous word meaning I want a pet kangaroo. So, yeah, I know, I was being silly. But no, it's place of the digging stick. Didn't know that. So, of course, the digging stick was one of the implements that the ancient indigenous peoples of Australia used to use to dig up food, grubs and other bush tucker, as we call it these days. So
it's probably worth mentioning for the listeners who are not in Australia that many of the Australian places have names that derive from the languages of the traditional owners of the land, the indigenous people of Australia, who had many different countries with many different language groups. And the origin of the names is not always that well known or understood, because during the invasion of Australia and during the events that happened all the way through to the 1970s, there was a fairly aggressive attempt to, even if you weren't wiping out the people, to get rid of the culture and get rid of the knowledge. Yeah. Now, I've just looked up Toowoomba, where I am, Toowoomba. I live about 20 k's west of there. Toowoomba is an indigenous name. It's a really interesting town because it's like the Florida of Queensland. All the old people come here to retire.
It's a lovely place.
It's a beautiful place because Queensland has a particular climate, but Toowoomba is a moderated version of that climate because it sits on the Great Dividing Range at about 700 metres above sea level. So it's not as humid as the coast. It doesn't get as hot as the coast. It has very lovely dry winters. Anyway, the name of Toowoomba is probably based on a word from likely the Gayabal or Jarawai peoples, not entirely sure. But if you look around for the origin of Toowoomba as a word, there's lots of suggestions. There is a suggestion that it was a word for swamp because Toowoomba sits in this swampy area on top of the hills. According to the Toowoomba Regional Council, it may have been named after a property in the area in the 1850s, or it may have come from an Aboriginal word meaning either place where water sits, which would be the swamp thing, or place of melon, or place where reeds grow, or berries place, or white man. There are other things saying meeting of the waters, or saying the name of Toowoomba may be an anglicised version of the word Boowonga, which meant thunder in the dialect of the Upper Burnett and Gayndah tribes. So we just don't know. And it does make me a little bit sad. We talk about Indigenous astronomy a bit and the wonderful work that Professor Dwayne Hamaker and his students have done over the years working with the Indigenous people of Australia. But it does make me sad how much of this knowledge is lost where you don't even know the origin of the name. So it's wonderful that in this case we actually know where the name comes from. And we can tag that. So when you're looking at the map of Australia, I think a lot of the places are unusual from the perspective of someone from an Anglo background or from a European background. It's because even though it's a primarily English-speaking country nowadays with that, Anglo heritage, a lot of the names are actually from the traditional owners, even if the heritage of that name itself is lost.
Yes, where I live, Dubbo is supposedly a Wiradjuri word for red earth because the soil here is red, which might sound horrifying to people. It is when you get a dust storm and everything turns red.
It's worse when it gets wet and you bring it in because the red soil marks everything up.
It's
dog goes out and gets their paws muddy and brings in red footprints.
Red footprints on a light-coloured carpet. No, terrible stuff. And, of course, one that relates to astronomy is Woomera, which is an Indigenous word for the implement they used to launch a spear. Rather than just throw the spear, they used to have a specially made, I suppose you'd call it like a handheld catapult, it flung the spear at greater speed and distance, and that's it was called a Woomera. And of course, Woomera Rocket Range is where Australia's early space efforts were launched from in South Australia. So it's fascinating history, really is. And
of course, the atlatl that I mentioned there, I just double checked because it's like I remember an atlatl being a thing that used for throwing spears. It turns out that was an Aztec implement that served the same kind of process. So the word atlatl apparently comes from Aztec.
Oh wow! Okay. Didn't know that. Back to you, Andrea.
Yes.
Now, two questions. Dark side of the moon, smoother. Now, I've always been aware that the side we can see is so rugged and pockmarked and mountainous.
Yes.
But the side that we cannot see, that Artemis 2 recently had a look at, and where the Chinese have been running around on their little scooters, it's smoother. Why?
Well, this is a weird one. So it looks more uniform when you look at it. And I'm saying that very carefully rather than smoother, because smoother invokes polished or smooth. Like your skin when you're a kid is a lot smoother than your skin when you get to my age and you've got all the wrinkles, right?
Yeah. Or the scars. See this one?
Yeah,
That's from a golf club. My neighbour hit me in the face with a 7-iron.
Yeah,
It wasn't malicious. It was the backswing. I was standing too close.
I was going to say it sounds like the adventures you have in Dubbo. You know, they do something to pass the time. The reason that I'm being careful in my wording in here and saying it looks more uniform rather than it's smoother is actually I don't think it is smoother, but I think it definitely does look more uniform. On the near side of the moon, it should be said that we're talking near side and far side. The dark side of the moon is simply the side of the moon pointed away from the sun, and that rotates around as the moon goes around the Earth, which is why we get the phases, right? If you're stood on the moon, you'll get, at a given location, 2 weeks of daytime and 2 weeks of nighttime. And when it's nighttime for you, you'd be on the dark side of the moon. But when the moon's new, the dark side points towards us. The far side of the moon always points away from the Earth. Now, on the near side of the moon, which is a side we're familiar with, the view we get is very non-uniform because we've got the mare and the non-mare regions. So the mare are the seas, which make up the man in the moon or whatever picture you have, which are these flood basalt areas. And then you've got the non-mare areas, which are more traditionally rocky object looking.
He's the drunk man in the moon here because he's upside down.
Absolutely. Yeah. It's those areas that make the drunk man are flood basalt outpourings on the near side of the moon that were formed early in the moon's formation. If you ascribe to the idea that there was a late heavy bombardment when the impact rate spiked, then they are thought to have formed there. But in actuality, evidence for the late heavy bombardment has pretty much dissipated. So the closer you are to impact studies and studies of the moon, the less strongly you hold to the idea the late heavy bombardment was a thing. But as with all science, the further you get from a certain expertise, the more out of date your knowledge is. So the late heavy bombardment is quite often still viewed as canon in a lot of areas, whereas those who are closest to the topic have a lot more doubt that it ever happened. But anyway, on the near side of the moon, you've got areas of the moon that didn't have a mare, didn't have a flood basalt outpouring, and you've got areas that did, and then overlaid on that, you've got some more recent impacts, which are the ray craters, where you've got weathered material on the surface that looks darker, and an impact comes along, digs through the darker material to the unweathered material below and splashes it across the surface. So the near side of the moon looks very non-uniform because you've got that disparity between the flood basalts and the non-flood basalt. And the non-flood basalt is an older surface because the flood basalt erased the evidence of what happened before. So there are slightly fewer impacts on the mare than there are on the non-mare because it's a younger surface. Prior to any spacecraft going to the moon, the assumption was the far side of the moon would look like the near side. But when we sent spacecraft there, we realised it doesn't. And that was a big puzzle for astronomers for a very long time, in that there are effectively no mare on the far side. There's little bits, but not very much. Now, the idea here is that when the moon formed, it formed as a result of a giant impact on the Earth. The moon accreted and initially was fully molten, and then it cooled from the outside in. So at a certain time in the moon's youth, the surface was very thin above a magma ocean, above a molten ocean. And at that time, small impacts wouldn't penetrate that crust, and you get normal craters, you get mountain ranges and all the rest of it forming. But when you got a really big impact, that will break through the crust, create a big impact basin that would then be flooded with flood basalt, which gave you this incredibly flat, smooth floor and erased all the evidence of the impacts before. Eventually, the moon cooled enough that that any molten material was sufficiently deep that even the biggest impacts would not cause these flood basalt outpourings, coupled with the fact that as the solar system aged, it cleaned up very effectively and the big impactors were effectively gone. So the big impacts were early on. So the idea was that the mare are caused by the very biggest impacts that will create impact basins that are hundreds or thousands of kilometers across, that are broadly circular in shape before other things happen, and that they fill with molten material. And the areas on the near side that are not in the mare are the areas that were not induced into one of these flood basalt outpourings. Effectively, they escaped being in one of the craters from the very biggest impactors. We thought that prior to going to the far side of the moon, you would have assumed that the far side would be the same, but it turns out that it's not. That was a real problem, because this idea that the impacts were big enough to punch through and flood to the surface should work all across the moon. So why then do you not get the flood basalt outpourings on the far side of the moon? There are kind of three explanations that have been put forward for this. The first of which is frankly bunkum. The idea that the near side of the moon faced the Earth and the Earth shielded it, and so therefore there'd be more impacts on the far side. Well, that just kind of runs counterintuitive. You'd say the far side experienced more hits, it gets more cratering. Well, I don't believe that for a minute, because the Earth is so small from the moon's point of view, it's barely a shield at all. But if that were the case, surely you'd expect more mare on the far side because you get more of these big impacts. So that to me doesn't work. So we can rule that out. The other answers are kind of tied together, but the idea is that the moon had a thicker layer above the molten layer on the far side of the moon to the near side. Two ways you can make that happen. One idea is that the heat from the young Earth, which would also have been molten at this time and being bigger, would keep its heat longer, so would be molten for longer. The Earth would be irradiating the moon. The moon would be close to the Earth when they formed, because it's moved away since. That radiative heat would have kept the near side of the moon hot for longer, which the molten material on the surface would have stayed for longer, but also it would have taken longer for the crust to thicken on that side. So therefore, the crust on the far side of the moon would have formed quicker and thicker. The other idea is that you get the same kind of effect from tidal forces, that the tidal influence of the Earth on the moon is stronger on the near side than the far side because the strength of tides falls off as distance to the power 4. So that's a very strong, very rapid effect.
Yeah.
Possibly both of those things to combine give you a crust around the moon that is thinner on the near side than the far side at all times as the moon cools on the interior, which means that the far side of the moon, the molten material was deeply enough buried quickly enough that no mare forming impact happened. You've got the South Pole Aitken Basin, which is the biggest impact scar on the moon. Doesn't really have much flood basalt in it, which either means that it is younger and therefore the interior had cooled enough that it didn't crack that egg, or that it was an area where the crust was thicker anyway, you know. So the idea is that the difference between the near side and the far side of the moon is down to the thickness of the crust when the biggest impacts were happening. And the idea that probably due to a combination of tidal effects and radiative heating from the incredibly luminous molten Earth, the near side of the moon stayed a thicker shell and therefore was more effectively punctured. And so the near side got the mare and the far side looks more like your typical rocky objects like Mercury, like a lot of the rocky moons and stuff like that in the outer solar system. That's the thinking there, but it is really strikingly obvious when you see photos of the far side of the moon and you're not told it's the far side of the moon, you assume you're looking at an object that is not the moon because it's no different to our experience of the moon.
Indeed. So part two of her question you've basically covered because of the deep impact.
A little
illustrations.
bit. Part two is a bit more complex.
So this is the one about shallow craters.
Why are craters shallow? And craters are shallow not just on the moon but everywhere. There is a boundary between what researchers describe as a simple crater and a complex crater. Okay. And the size at which you get that boundary varies dependent on the strength of material that's impacted and also the mass of the planet and therefore the strength of gravity. So I believe on the Earth it's about 8 or 9 kilometers. For the moon, it's about 18 kilometers. Smaller than that, you get a simple crater that forms, which looks very similar to what you'd get if you almost just threw a rock really hard into sand or something. You get the typical bowl-shaped crater, like Meteor Crater in Arizona. Really nice example.
Yeah.
At a size above about, like, say, 8 or 9 kilometers on Earth or above about 20 kilometers on the moon, you get to the domain where you get a complex crater. And complex craters are characterized by having quite often central impact peaks, but also having these much shallower depths compared to their width. You know, and it's particularly true for the mare where they're flood basalts, where you have a very shallow crater for the width of the crater. But it's true even if you look at 20-kilometer craters on the moon. And there's a beautiful photo, incidentally, if you look on some of the NASA images, there's a beautiful photo of the crater Aristarchus taken by the Lunar Reconnaissance Orbiter. And that shows this kind of terracing around the walls, the central peaks. And so there's a few things going on here that contribute to why what we describe as being, complex craters are actually shallower compared to their width than the simple ones. And there's a few things that have been suggested to this. So complex craters have depths that can be a 15th or 25th or even less of the crater width, which looks very, very shallow. Now, there's a few things proposed in for this. Firstly, when you form a bigger crater, the walls can slump in. So material slides, and gradually you get this material from the edges sliding into the middle. And if you look at that photo of Aristarchus, it looks very much like that's happened. You see evidence of landslides that have filled in the crater and made it shallower. The other thing is, though, craters that big are large enough to render the material where the impact happens molten. And in other words, the material can flow like a liquid rather than behaving like a solid material of your desk.
Well, you can still see a rebound point in the middle of the crater too.
So that's it. So the stuff at the middle, the central peaks, are thought to be rebound of this fluid material springing back before it freezes solid again effectively. And then the flat base of these craters that makes them shallower is because you make a pool of liquid that spreads out and settles. And so therefore you get these shallower things, whereas with smaller craters, you don't get to that point, so you get much more material behaving more as a solid than a liquid, effectively. So the thinking is for these complex craters, and like I say, for the moon, I think the size scale is, 18 to 20 kilometers, something like that. It's a point at which you transition from simply behaving as a solid to the surface behaving in more of a liquid fashion. You get complex craters having central peaks, they have terraces, they've got flat floors. The more massive the object, the smaller the boundary is, because gravity has a role in this.
Yeah.
And then you get the basins, which are even bigger, and there where you get the flooding from basalts, which makes them even shallower compared to their width. So there is some beautiful complexity of this, where it's all to do with the physical behavior of material and how that changes as an impact gets larger and larger, and therefore more and more damaging and energetic. Now, NASA have a MarsEd website where they actually explicitly say, if you Google for this, it's marsed.asu.edu and then a really long string afterwards. It's a Mars education thing at Arizona State University. And I'll just quote here. Compared to simple craters, complex craters also generate a lot more impact melted rock. This typically flows and pools like lava to form a sheet that covers a shattered rock known as breccia on the crater floor. The crater's inner walls may slump downwards, rotating backwards in blocks, which can widen the crater's rim and line the inner walls with terraces. But as a result, complex craters look shallow. They have rim diameters about 30 times greater than their depths. By comparison, simple craters are about 5 times wider than they are deep. Earlier on, it said the more energy an impact delivers, the bigger the cavity on the ground. But immediately after the blast, the center of the cavity begins to rise as rocks rebound from the shock. That's what gives you the mountains. This uplift gives you a central peak or cluster of peaks. So that's a really nice way of condensing my lengthy, waffly answer into something a bit more simple and straightforward.
Fair enough. Okay. Now, Andrea, you can believe all of that, or you can go with my theory that the Lunar City Council were on strike and they didn't finish filling the potholes. I go with option 2. Andrea, thanks for your question. Great to hear from you. Thanks for explaining Wanneroo. This is Space Nuts, a Q&A edition with Professor Jonti Horner and Andrew Dunkley.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem. We've had a main beam bus undervolt.
Roger, main B undervolt. Okay, stand by, 13. We're looking at it.
Space Nuts.
Our last question comes in 2 parts, and it comes from Eli. Hello from Coachella Valley in California. Wasn't Coachella in the news recently for some big soiree that happened there? Yeah. Big event. Anyway, he says the grasshoppers have decided to invade. Believe it or not, Eli, exactly the same thing is happening where I am. We have locust plagues once in a blue moon, and we had a little one recently. Wasn't too significant. But I have discovered with locusts or grasshoppers or whatever you call them, wherever you are, that if you drive over 50 kilometres an hour, they splatter. If you drive under 50 kilometres an hour, they bounce off. Important safety tip, especially because when they splatter, they stink. and it's very hard to get off when they're dry.
I'd love to have a swapsy where we've had an incredibly dry last few months here. It's been our wet season and we've had 40 mil of rain in 4 months.
Wow.
Which is, hooray! You know, that's really what you want in your wet season when the dry season is about to start. But what that means is that we're probably going to see yet another mouse plague. And mouse plagues are sad because in the times that are good, mice reproduce like crazy, but then you get the boom busting. And so you start getting lots of them coming to your house. And I'm soft-hearted. I don't want to hurt them or do anything, but at the same time, I don't want them pooing on everything in my kitchen.
Yeah.
So we're getting mouse plague times. So I suspect that locust plagues are horrible, but mouse plague is an entirely different horror. And
Mouse plagues are worse.
Yeah.
Because the mice try to find somewhere to hide inside. Locusts only get in if they've got an open avenue. Otherwise, they just stay outside and, you know. And they also are very disturbing when you're trying to putt on a golf course.
Oh, absolutely.
They just get in the way.
The mice just
sorry.
You walk into the kitchen at night or you walk somewhere and you just see something move in the periphery of your vision, and that's always a little disturbing.
Yeah.
Or,
yeah. Well,
yeah.
we're talking mouse plague here as well, so we could have both. But our last big locust plague, it was so big the birds just got fed up with eating them, so they gave up as well. It's very weird. Eli, what are you asking us? Since you mentioned a paucity of questions, I hope you don't mind a twofer. Okay, we've got 2 questions then. When the solar system formed, I always imagined the inner rockier planets as having more heavier elements due to their greater mass and gravity, and with lighter elements collecting more in the outer gas giants. But then I realised, isn't the sun mostly hydrogen, the lightest element? Now I'm confused. That's his first question.
Yeah. So
and this is your bullpen, isn't it? This is your area of expertise.
This is much more my comfort zone, so this is lovely. It's really.
I hope you realised I did try to find questions that worked for you.
No, that's all good, and it means you can leave the cosmology ones for when Fred gets back as well, which is great. Now, this is a lovely question, and it speaks to how our understanding of how planets form has changed over time, and we've now got quite a high level of complexity in the ideas we have behind planet formation. But a really fundamental part of it is that everything in the solar system to first order has the same composition as the sun, because we all form from the same material. We form from an enormous cloud of gas and dust called a giant molecular cloud that collapsed under its own gravity. You got effectively the protostar sun forming in the middle with a disk of material around it we call a protoplanetary disk. And in that disk, you have solid material and gaseous material going around the sun, orbiting the sun, collapsing to a disk because of the conservation of angular momentum. So kind of where the Earth is, material was whizzing around at about 30 kilometers a second, but individual dust grains that were next to each other were both moving at about the same speed. So very little difference in speed between the particles, even though they're going really quickly. Now, the further you are from the sun, the colder the temperature is in that disk. And every single material you can think of has a sublimation temperature. Below that temperature, it will be solid, and above that temperature, it will be gas. Reason I'm not talking about liquid is in order to have a liquid, you need pressure. And in this case, you don't have any, or you don't have enough. So you either have solid or gas.
Yep.
If you are gas, then you don't form planets initially. If you're solid, you can do. So what happens all through this disk, for a variety of different bits of physics going on, you get whatever solid material you have at that distance colliding, sticking together, forming bigger bits. And so you get from millimeter to meter to kilometer to planet-sized bits of debris. As you get bigger, gravity can start taking on a role and start pulling in a bit of extra stuff so you can feed quicker. Plus, if you're bigger, you've got a bigger cross-section, so you hit more things to devour them. So you get this process where you get lots of small things making a few bigger things, and the big ones tend to dominate. So a thing called oligarchic growth is the idea. And you form planetesimals and then oligarchs, which are protoplanets, and a few of them collide, all the rest of it. If you are far enough from the sun, you're beyond what's known as the water ice line. Now, that's the point at which the temperature is below the sublimation point of water. So instead of water being a gas or a vapor, it's a solid. Now, we always imagine water being quite scarce, and I just said we've had 40 millimeters of rain in the last 4 months, so water's very scarce here. But in terms of compounds in the universe, water is one of the most abundant things there is. because it's a combination of hydrogen, which is the most common atom with 75% of all atoms, and oxygen, which is the second most common atom with about 1% of all atoms. Put hydrogen and oxygen together and you get water. So in the protoplanetary disk around the sun, water was probably about the most common species other than molecular hydrogen, and helium atoms. Lots and lots of water. Now, where the Earth formed, it was too hot. So you don't have water as a solid. So you form the Earth dry. There's no solid water to accrete. You might get a little bit of water as a gas that is trapped in the solid material, which is why people think most of the Earth's water was delivered from further out, because if far enough out, you form from primarily water with everything else added in. So the inner solar system, you don't have that water to accrete, so you're limited to the things that are solid at higher temperatures. So you're limited to accreting from rock and metal. So you get telluric planets, or is the archaic way of saying it, or terrestrial planets. Beyond the ice line, water ice dominates the solid material. So you've got a lot more to feed from, so you grow more quickly. And you can get more massive planets more quickly, which is where Jupiter and Saturn come in. Now, there's a lot of discussion about how they may have migrated through the nebula or all the rest of it, and the subtleties of the formation. In other planetary systems, we have planets like Jupiter orbiting their stars every 4 or 5 hours even, but we don't think they formed there. We think they migrated in. So you form beyond the ice line more quickly because you've got more food. And you can grow to masses like 10 or 12 Earth masses while there is still an abundance of gas around. That gas doesn't hang around long, because once the sun fully turns on, after a few million years, it blows the dust and the gas away, and you're left with whatever's left over. But if you form to be 10 or 12 Earth masses, before the gas is blown away, suddenly your gravitational pull is strong enough to hold on to hydrogen and helium. If you're less massive than that, then the escape velocity of a hydrogen or helium atom will be higher. Sorry, the escape velocity of your object with that mass will be lower than the speed at which hydrogen and helium atoms move at that temperature. So you can't hold on to them. They just escape because of their motion, because of the temperature they're at. When you get to 10 or 12 Earth masses, the escape velocity from your core is higher than the speed at which hydrogen and helium is moving, so you can start to capture that. And like I said, 75% of all atoms are hydrogen, 24% of all atoms are helium. 99% of the mass of the protoplanetary disk, or 98% maybe, is inaccessible till you get to that mass, and suddenly you've got this whole new food source. So you quickly devour all the gas around you until you open a gap in the disk. And that's how you get the gas giant planets Jupiter and Saturn. With Uranus and Neptune, they formed further out. They had a lot of abundant volatile material, but they didn't really get massive enough to devour the gas before the gas was blown away. So that's why you get the ice giants. And that is partially because they're further away, they form slower. There are some arguments that Uranus and Neptune may have formed between Jupiter and Saturn and been scattered out. But on a broad brushstrokes sense, in our solar system, we don't think a huge amount of migration happened, which is probably down to the mass of the protoplanetary disk, not compared to the hot Jupiter systems we find elsewhere. So the planets we see today are within a factor of 2 or 3 times the same distance they were when they formed. Jupiter might have migrated in and back out. Uranus and Neptune probably formed significantly closer to the sun and migrated outwards. But you've got Jupiter and outwards forming in the ice-dominated area, the terrestrial planets forming in the area without ice, and therefore they're dominated by the rock and the metal. So you've like got this filter. So if you look at the fraction of iron compared to carbon in the Earth, or pick any 2 things that would have been solid, silicon versus iron, phosphorus for whatever, things that were solid, the abundances of those things in all of the planets relative to one another will be effectively the same as the abundance in the sun. But the terrestrial planets weren't able to capture the things that would have been gas at their distances, other than that what was delivered later on, and weren't able to hold on to hydrogen and helium. So you get that chemical differentiation as a result of the location of the solar system. There's a bit of added complexity because chemistry happens, and you'll get isotopic variations and stuff. But in broad brushstrokes, the reason the terrestrial planets are dominated by rocky and metallic material is they never got massive enough to capture the gas, and they formed close in where ice wasn't around. That's effectively how it happened. So what this question from Eli is doing is actually effectively describing the logic process that went into how we first began to understand planet formation. Because I said before, I think, on a previous episode, astronomy is not an experimental science in the way that every other science is. You know, biology, chemistry, physics, you want to figure out how something works, you can do experiments. Astronomy is an observational science. Everything's so big and so far away, we can't put it in a lab and smash it. We instead play detective. We look out at the universe and we gather clues and we ask questions, exactly like the question Neil has asked here, which in its fundamental sense is, why do we have rocky planets close in and gaseous ones further out? Why are there different compositions when we should be the same composition of the sun? We then come up with explanations for that are our theories. And to be a good theory, you can't just say, I explain everything we see. You've got to make predictions. As we find more things, we will observe this. And that's how we test that theory. And we test it by this interplay between observation on the one hand, theory on the other. And what Eli's asked here is essentially the questions that people are asking that led to our current understanding of planet formation.
And yet, we see other solar systems with exoplanets that defy what we think is normal. You have gas giants close to the parent star and rocky planets further out.
And that's how we...
Is that because they've just drifted that way?
It's complicated. So our ideas of how planet formation happened have undergone quite a few major evolutions as we found planets around other stars. So in the early 1990s, I had a couple of talks at my local astronomy society in the UK from Professor Wolfson of York University. And Professor Wolfson was an advocate of an entirely different formation scenario for the solar system. I think he was someone who argued that the solar system formed through an encounter between the sun and a young protostar, where materials pulled out of the sun into a massive tongue, and that tongue condensed into planets. Back then, that idea was going out of fashion because we'd found a few debris disks around stars like Vega, Fomalhaut, Beta Pictoris, but it was still considered possible. Yeah. Such an event would be incredibly, vanishingly rare because stars getting that close together within one another's Hill's sphere is incredibly unusual. Very, very rare. And so what that would predict is, if that theory were correct, we would be almost unique. There will be vanishingly few planets around other stars because the scenario you need to form planets would only happen very rarely. On the other hand, there was the idea, which dated back to initially the 1700s and beyond, the Laplacian model, the circumsolar disk model, which has evolved into what we have now, which suggested that as part of star formation, you get a disk of material around a star and planets form from that disk. Disks are a natural byproduct of the formation of stars, therefore planetary systems should be common. Both scenarios, with a bit of fudging and fiddling, could perfectly explain how the solar system looked and have been finessed to reproduce the solar system. But the test was always going to be, which of these theories is correct will depend on how many planets we find around other stars. If planets are rare, then maybe the solar system is the result of a tongue being pulled out of the sun. If planetary systems are common, that cannot be the case. So that was a test that was done there. So when we found the first planetary systems around other stars and we found that planets are ubiquitous, that was kind of the death knell for the Wolfson type model of a tongue being sucked out of the sun and forming planets. But it kind of confirmed the Laplace model, but it also threw a spanner into the work in that the variation of planet formation of that disk model suggested that you would always form planetary systems with rocky planets in the middle and gas planets on the outside because it had been developed to explain the solar system. When you found planets that were hot Jupiters, they don't fit. They're planets of massive Jupiter close to their star, which brought in the concept of inward migration. Now, it's an interesting time because in the same few years, people had started to realize that in the solar system, there was clear evidence of planetary migration for the giant planets, primarily that Neptune had migrated outwards, carrying Pluto with it to form the Plutonos. So you've got these seminal papers by Renu Malhotra talking about the outward migration of Neptune being evidenced in Pluto and the Plutonos, predating the discovery of the first exoplanet. And one of my gripes through my career has been that the exoplanet community primarily came from binary star astronomers, not from solar system astronomers, so reinvented migration to some degree and assumed that we had no evidence for it in the solar system. And in parallel, the solar system community was working on migration separately. But the discoveries of planets around other stars over the last 30 years and more, which is a great scientific revolution we've lived through. You know, you and I grew up in a world where the only planetary system we knew was our own. And kids today grew up in a world where we know planets are ubiquitous. That's a cataclysmic shift to have lived through.
Yep.
That living through that has proven an incredibly fertile testing ground for our theories of planet formation. Turns out that Laplace theory, the disk theory, was a good way of the way there. So it hasn't been totally discarded, but it's been refined and we've learned more about it. And that continues to the current day. The refinements are leading to all sorts of complexities, like invoking streaming instabilities to concentrate pebbles at certain distances and all sorts of subtleties to try and address some of the pitfalls of how on earth do you get from millimeter-sized to meter-sized objects when collisions should become destructive? All sorts of things like this. And it's through those observations that we get to improve and refine our models. We're not going to end up throwing out the disk model now because we can see the disks that form planets around other stars because our telescopes have got that good.
Yep.
And one of the predictions would have been, prior to them getting that good, if the disk model is right, when we look at places like the Orion Nebula with a sufficiently good telescope, we should see protoplanetary disks, proplids. Then the telescope's got good enough and we can see them now. We've even got to the point now where we can actually even observe fine structure within them to see the gaps that giant planets open up, to see the spiral waves that are sometimes induced by a massive planet being born. So we're now not only inferring planet formation from the plethora of planets that we're discovering around other stars and from the fine details of what we know about the solar system, but we're actually also getting observations of the disks in which it's happening that are providing extra information to improve those models. It's
fascinating. So you can simply say there's no one-size-fits-all way of this happening. It's circumstantial.
It's a broad thing versus a narrow thing. So in a broad sense, planets forming a disk around a star, natural product of star formation. There may be occasional ways other planet formation mechanisms happen, like the planets around neutron stars are thought to probably be second-generation planets. They're probably material formed from a disk that formed around the neutron star after the supernova and formed a new generation of planets. You might eventually one day possibly find planets formed from material pulled off a star. The very most massive planets, some of them will probably have been formed more like binary stars than actual planets, which we talked in the past about when is a brown dwarf not a brown dwarf.
Yes.
But the broad brushstroke thing is fairly well established. But and every single planetary system is unique. Everyone has unique circumstances. Some disks around stars are more massive than others. Not every star will have an identical disk. Some disks get truncated because a passing star strips material away. Some disks get ablated away because there's a massive star nearby whose radiation pushes material away. You then even get impacts on the chemistry. So there's really fascinating studies looking at the solar system that suggests there was a nearby supernova when the planets were forming that injected highly radioactive short-lived aluminium-23, I think it is, that gave an extra spike to the melting of planetesimals that led to some of the subtleties of how the solar system looks. There are indications even, I think, that the amount of gold in the solar system is unusually high compared to the standard metallicity, the amounts of everything else, which is indication of pollution from two neutron stars colliding within 10,000 light years of where the solar system would form, about 100 million years before we formed. So even that level of injection of material is unique from one system to the next. And that's why every planetary system, like every person, is unique.
Fascinating. Fascinating. Aren't you glad you asked, Eli? And Eli's second question, I recently read that some star systems are zipping through their galaxy orbits at incredible speeds of 1,200, I'm assuming that is kilometres per second. That's 0.4% the speed of light. That got me wondering, how fast could our solar system get going before we started noticing things going wrong? You know, the windows rattling and such. I think we've had questions similar to this. I think we did one recently where we talked about how fast the Earth would spin before things started to go horribly wrong. This is a question of similar ilk. I hadn't heard about those sorts of speeds being detected by
stars. There'd be stars very near the supermassive black holes at centres of galaxies, and that kind of speed doesn't surprise me. Now, my immediate take on this is that we wouldn't notice effectively. So the reason that I'm saying that, and I stand to be proved wrong when you get up to relativistic speeds, because my knowledge of relativity is not sufficiently good to be absolutely certain on this. If you are moving at a substantial fraction of the speed of light, I don't think we'd notice anything wrong in terms of the Earth moving around the sun, because we'd still be going around the sun at 30 kilometers per second while we're both moving around the galaxy at relativistic speed and accelerating. What we might notice then is time dilation in the fact that the external universe appears to be moving quicker than it should do. So we might see the effect of the fact that our time is slowed if we were going around, just the same as, you see the stuff about people orbiting a black hole at high speed or whatever, or falling into a black hole. But in terms of us noticing in terms of physical phenomena on Earth that we're traveling at a certain speed around the galaxy, I don't see a way that would work. And the reason for that is that there's no resistive medium. We think about this thing happening because when you're driving in your car, the quicker you get, the more obvious your speed is because of the rattling and the wind resistance and the noise. But that's all down to your interaction with something that isn't moving at the same speed you are. If you're in the International Space Station and you're orbiting the Earth at several kilometers a second, you don't feel the space station rattling because it's going really quick, because it's moving through the vacuum of space. So it's not interacting with anything. If you're coming back into the atmosphere, you rattle and rumble and all the rest of it. We saw this with Artemis 2, because you're slowing down. You're experiencing acceleration, you're experiencing buffeting. Yep. So to me, if we are moving as a planetary system around the middle of the galaxy at very high speed, our planets would still be orbiting the sun in the same way and we wouldn't notice any difference. What would happen, though, is we'd be moving through a much, much denser stellar neighborhood. The sky would be immeasurably beautiful but challenging, but also close encounters between stars would be very common. And so it may well be that the stars would be so densely packed that eventually we'd have a stellar approach that would be so close the solar system would be disrupted, and we'd certainly notice that. Also, if we were injected to there from where we are now, there would be a period of adjustment where the Oort cloud would be heavily destabilized and we'd have catastrophic levels of impacts from the comets being scattered. But eventually they'd all be gone, so it wouldn't be a problem. So we'd notice it from the point of view of...
Tell that to the dinosaurs.
Oh, absolutely. Long may they rest. But it's one of those things where if we were there and we were transported there from now, what we'd notice is that the sky looked very different. If we were moving at that kind of speed, in that denser stellar neighborhood, the proper motion of stars would be apparent to the naked eye over human timescales, which it's not for us. Barnard's star, which is the fastest moving star across the night sky, will cross the diameter of the full moon in a century, very roughly. That means if Barnard's star was bright enough to see with the naked eye, we'd have known about proper motion earlier because it would be obvious, but it wouldn't be the kind of thing you'd notice from one year to the next. Whereas if we were in the middle of the galaxy going around the supermassive black hole at that ridiculous speed, stars will be closer together, which magnifies the effect of motion from our perspective. Also, they'd be moving quicker, which means that the motion is quicker from our perspective. And you probably have proper motion being visible on human timescales to the point that the constellations would move rather than being fixed patterns. That you'd notice. You wouldn't feel the acceleration. You wouldn't notice anything's wrong, but we probably wouldn't be there if the sun had been there for a long time, because it's a very inimitable environment for life, because there's a lot of stars close together, a lot of massive stars, a lot of supernovae. It's probably a bit of a dead zone.
Aha. Okay. All right. Thanks for your questions, Eli. And yeah, I love that second one. I love what if questions. Yeah, we've been getting a few of those lately. It's they're just such great fun. Thanks to Nick and Andrea as well for contributing. And if you would like to send us a question, please do on our website, spacenutspodcast.com, spacenuts.io. Click on the AMA button at the top. Ask Me Anything is what that stands for. And you can send text and audio questions. Don't forget to tell us who you are and where you're from. And while you're there, have a look around, check out the Space Nuts shop. Maybe you'd like to become a supporter, sign up for the Astronomy Daily newsletter, all sorts of things to see and do on our website. And please leave reviews wherever you listen to Space Nuts. We appreciate that as well. And we appreciate you, Jonti. Thanks so much for your input today. Fantastic.
Oh, it's always a pleasure. And yeah, fabulous questions. Really enjoyed them.
Me too. And we'll catch up with you very, very soon.
Yeah, I look forward to it. Thank you.
Professor Jonti Horner from the University of Southern Queensland, where he is a professor of astrophysics. And thanks to Hugh in the studio, who couldn't be with us today because time moves slower for Hugh. So he'll be joining us in a couple of thousand years. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.